네, 여러분 안녕하세요. 지난 시간에 이어서 수업을 계속 이어나가 보도록 하겠습니다. 이번 시간에는 여러분이 이제 물리화학 혹은 또 이런 연력학 중에서 여러분이 실제 나중에 뭐 실제 여러분이 어떤 그 전공을 살려서 일을 하실 때 가장 많이 접하시는 그 단어 중에 하나인 깁스 프리 에너지에 대한 내용을 얘기를 좀 해보도록 하겠습니다. 그래서 이런 자유에너지 관련해서 헬몰츠 에너지와 깁스 프리 에너지가 있는데 뭐 두 개가 사실 되게 많이 연관이 돼 있고요. 특히나 이제 깁스 프리 에너지 같은 경우에는 뭐 다양한 어떤 반응이라든가 어떤 다양한 재료를 만드는데 되게 많이 활용이 되고 있죠. 그래서 그 내용에 대해서 오늘 같이 이야기를 나눠보도록 하겠습니다. Okay, so let's start this today classes. So today we will discuss about this Helmholtz and the Gibbs energy. So these two terms is the widely used for the many application area. So especially if you have some kind of works related to your the major, then you will frequently see this kind of terminology of, especially for the Gibbs free energy. So I don't say this Gibbs free energy is the most important terms in this physical chemistry, but I just let you know. So if you have faced this kind of terms in your life, then please remember this class materials, and then you can have easy mind to access that kind of problems. Okay, so we will learn about this Helmholtz and Gibbs energy, and what is the Helmholtz and Gibbs energy. We will talk about that things. Okay, so let's start first with this key point. So the first, we will start with this Clausius inequality, which we already learned in the previous classes. So this Clausius inequality implies a number of criteria for this spontaneous change. So we have learned this one. So this Clausius inequality is kind of criteria which can evaluate that kind of a reaction will be the spontaneous or not. So this is one of the fundamental the equation for that kind of the evaluation. So this Clausius inequality implies a number of criteria for spontaneous change under a variety of conditions, and that may be expressed in terms of a property of the system alone. What this means? So they are summarized by the introducing this Helmholtz and Gibbs energy. So what this means? So as we learn, this Clausius inequality is kind of a criteria for this spontaneous change evaluation, which is especially for under various conditions. And depending on the kind of a condition, this Clausius inequality can be summarized as this Helmholtz or Gibbs energy. So we will learn about how this Clausius inequality can be transformed to this Helmholtz and Gibbs energy. So this is the basics. So what can I say? The spontaneous process at this constant temperature and constant volume is accompanied by a decrease in the Helmholtz energy. So what this means? To do this spontaneous process, especially at this constant temperature and constant volume, then this can be summarized as this Helmholtz energy decreasing. So if this Helmholtz energy is decreased, then the reaction will be spontaneous at this constant temperature and volume. So this is the first definition for this Helmholtz energy. And the change in the Helmholtz energy is equal to the maximum work accompanying a process at constant temperature. So what this means? So the delta Helmholtz energy is the maximum work at constant temperature. So so we will talk about this, how the kind of definition can be derived through this Helmholtz energy. So anyway, there's a two important definition. Actually, if you remember the two things, actually you that's actually the half of this class actually. So all this kind of detailed steps, I don't let you. I don't force you to remember all that kind of derivation process of the kind of equation, because there is a lot of, how can I say, the assumption, and also to get this final form of this kind of equation for this the terms. Yeah. So what I mean is can I say? So the key things is I don't want you to remember all this kind of derivation process, but at least you have to remember this the fundamental concept of this Helmholtz energy and what this kind of Helmholtz energy can express. So that things is important, not that kind of the mathematical derivation process is not important for these chapters. So anyway, we will learn about the kind of derivation process, because as I always told you, how can I say, the undergrad course is kind of step to the how can I say, how can I say, the building your kind of a common sense for your major. So that's why we learn about all the kind of details. But in the kind of because this after this undergrad course, you have no time to study about this kind of in-depth things. But so that's why we at least we discuss our study about the kind of details in here. But the fundamentals of this chapter is not the kind of mathematical derivation process, but you have to understand what the kind of Helmholtz energy is the stand for, or the meaning of this kind of a concept should be understood. Okay, so anyway, these two things, I'm sorry, so I would like to read again. So this is two things is the important concept for this Helmholtz energy. So the first is the spontaneous process at constant temperature at volume is accompanied by a decrease in Helmholtz energy. And the change in Helmholtz energy is equal to maximum work accompanying a process at constant temperature. So this is all for this Helmholtz energy. And we will also talk about this Gibbs free energy. So what is the Gibbs energy? So the Gibbs energy is, can be derived in a similar way with this Helmholtz energy. So Gibbs energy is the spontaneous process at constant temperature. It's the same. but at the constant pressure, it's accompanied by this decrease in the Gibbs energy. So what is the difference? Helmholtz energy at this constant volume, and Gibbs energy is at constant pressure. So at this constant pressure, the spontaneous process is accompanied by a decrease in Gibbs energy, and constant volume, the spontaneous process can be evaluated by using this Helmholtz energy. So in a similar way, the change in the Gibbs energy is equal to maximum non-expansion work accompanying a process at constant temperature and pressure. Right? So non-expansion work. So generally, when we talk about the kind of internal energy, we usually talk about this expansion work. Maybe you might remember or not, but yeah, even though you cannot remember, but we learned these things in the summarized first law. So anyway, so there is the expansion work and there is also non-expansion work. This is kind of how can I call this? Is kind of additional works, such as some electrical energy, works by the electrical energy, or some kind of surface tension, or that kind of things, which is not the volume changing. Expansion work is the volume changing. Non-expansion work is the different types of additional works. So the maximum non-expansion work accompanying a process at constant temperature pressure is equal to the Gibbs energy change. Right? So this is the two things we will learn through these classes. So actually, yeah. So these two things we will learn about. Okay, so for your the gentle reminder, so I will write again what is the Clausius inequality. So we already learned about this Clausius inequality to evaluate this spontaneous change of the system. And how can we derive this Helmholtz and Gibbs energy from this Clausius inequality? So such things we will do it from now on. Okay, so let's talk about this criteria for the spontaneity. So this is the Clausius inequality. So from this Clausius inequality, we can derive this Helmholtz and Gibbs energy. And these two things is depending on the condition of the system. So if there is the constant volume, and there is also constant pressure. And as I told you, this constant volume is related to this Helmholtz energy, and constant pressure is related to this the Gibbs energy. So because at this constant volume, so the heat applied to the system is equal to the change of internal energy. So we can say you can change this Clausius equality as this kind of form at this constant volume. So that's why we have this ds minus t over du equal larger than 0. So that's why we can simply ds t over d mu. Then we can put this one here, and we have t ds equal du, right? So in this system, we already set this condition as a constant volume. And in this kind of situation, if the mu equal 0, then TDS equal will be larger than 0. And since T should be larger than 0, that's why we can say ds equal 0 when internal energy 0, internal change and volume change is 0. So that's why we have this kind of conditions. Right? And if ds equal 0, then internal change will be smaller than 0. So that's why we can say the mu when s and v, the s and the v equal, when the s and the v is 0, will be below than 0. Right? So this is the one conditions for this Helmholtz energy. So anyway, we can rearrange this equation as this one put here. Then we have the mu minus TdS will be 0 or below 0. And we define this internal energy minus Ts as A, and this called as the Helmholtz energy. So the change of dA, Helmholtz energy dA equal the mu minus TdS. So for the criteria of the spontaneous change at this constant volume and constant temperature at the certain temperature should be dA equal below 0. Right? So now we learned about what is the Helmholtz energy. So actually how can I say, it's kind of a definition of Helmholtz energy. So now this is the important terms for this Helmholtz energy. So from this criteria for the Clausius inequality, we just set up this certain condition, and then through the certain condition, we can get this kind of relation, and we define this kind of relation as a Helmholtz energy. And then using this Helmholtz energy, we can also make this kind of spontaneous change evaluation, especially at this certain condition, which is that the certain constant volume. But this means there is no volume changing. So this is the Helmholtz energy, right? And in a similar way, we can also define this Gibbs energy. So in this Gibbs energy, we have a condition, which is that the pressure is a constant, right? So at this constant pressure, this heat can be defined as the dH, that is the enthalpy. So we can say this ds minus T over dH will be 0 or larger than 0, right? So that's why in the same way, ds equal T dH, and just simply move this one, and then T ds equal dH, right? Which, when this pressure is the constant. Okay, so we can also make some kind of a certain condition when this dH equal 0, then T ds will be 0, and T will be larger than 0. So that's why ds at this constant H and pressure should be larger than 0. And ds equal 0, when ds equal 0, then th will be smaller than 0 at this constant entropy and pressure, right? So especially for some kind of really certain condition, then we can also have this kind of relation, right? So anyway, so we will rearrange this equation as move this TdS over here. So then we will have dH dH minus TdS will be smaller than 0, right? So we just simply define this H minus Ts as Gibbs energy, and dG equal the change of Gibbs energy will be the H minus TdS. So this is the definition of Gibbs energy. So criteria for spontaneous change when the pressure is a constant, we can simply find this Gibbs energy change, and if this Gibbs energy change is below than 0, the reaction will be a spontaneous change. So meaning of this Helmholtz energy and Gibbs energy are that, I mean, is that before this spontaneous changeover reaction, the Gibbs energy or Helmholtz energy should be decreasing at a certain condition. So especially at the constant volume, the Helmholtz energy should be decreasing, and at the constant pressure, the Gibbs energy should be decreasing. So if you have some kind of, I mean, if you face some kind of problem, you first have to define your problem, what this means. So where your problem is this put on. So especially your problem is has a condition of constant volume, then you have to use this Helmholtz energy for evaluating your the spontaneous changing. And if your problem the occur at this constant pressure, then you can simply use this Gibbs energy for evaluation of your the reaction, whether this is spontaneous change or not. So this kind of things can be done by using this Helmholtz energy and Gibbs energy. So yeah, so this is the fundamental definition of Gibbs energy and Helmholtz energy. And let's talk about a little bit more about this Helmholtz energy and also Gibbs energy. Okay, so there is some remarks on this Helmholtz energy. So what this means? So it's just kind of similar explanation. So now we know that this Helmholtz energy change is the du minus TdS. So now we know this definition. And dA can be below zero. So what this means? So tendency to lower A is solely a tendency towards a state of greater overall entropy. So what this means? So the how can I say? So let's see here. For this spontaneous change, we have to decrease this Helmholtz energy, right? So what this means? So then to decrease this Helmholtz energy, then we can simply think that this we can just simply decrease this internal energy. Then this Helmholtz energy can be decreased. But in the real system, it's not the kind of a decreasing of Helmholtz energy. It's not the result from this the decrease of internal energy, but it's mainly result from this increase of entropy, right? So this is what that means. Right? The how can I say? Right? So so this system means, I mean, the tendency to decrease this Helmholtz energy. It's not from this decreasing this internal energy, but it's a tendency toward state of greater overall entropy. So tendencies toward increase this entropy, right? So that's why. So this is the main remarks for this Helmholtz energy. So ds is the entropy change of the system, right? You know this one. And so that's why, and not that's why, and because this kind of a meaning, so T over du, so why this kind of comes from is the here. This one, this one is not simply change of internal energy, but it's about this entropy change of a surrounding. So in a spontaneous reaction, the tendency is decreasing this Helmholtz energy is about this increasing this entropy. So that things is the saying about this Helmholtz energy. Okay, so another thing is we can also define this maximum work by using this Helmholtz energy. So I'd like to start with this definition of this maximum work in terms of this Helmholtz energy. So the maximum work can be defined as the change of Helmholtz energy. So what this means, the change in the Helmholtz function is equal to this maximum work accompanying a process at this constant temperature. So how can you say like this? So there is some kind of derivation process to define this equation. So let's do that things together. So to demonstrate that maximum work can be expressed in terms of the change in Helmholtz energy, we combine this Clausius inequality, which is the ds is larger than T over dq in terms of TdS, so dq. So what I mean, just simply move this one. And with the first law, which is the du equal dq plus dw, right? So because then we have this one, right? Then we can simply put this TdS here. Then we have du equal TdS plus dw. Why du is the below than this one? Because this dq equal lower than TdS. That's why this TdS value, this one, so larger than dq. So that's why if we replace this dq with this TdS, then du should be lower than this term. So this is the explanation. So du is smaller than the term of the right, right? Because we are replacing by dq as TdS, which in general is larger, right? Because dq is a TdS. So we can simply this equation rearrange it to this like this. So we can simply move here. Then dw equal du minus TdS. Equal or larger than du minus TdS. We have this one, right? So maybe you might remember that when we study about this the internal energy, we learned about this work usually right. So it follows that the most negative value of dw. So what means it? So the smallest value of dw will be the maximum work. So the most negative value of dw and therefore the maximum energy that can be obtained from the system as work is given by dw max, so du minus TdS. Right? So because it's constant temperature, it's a dA equal du minus TdS. So we conclude that the Wmax equal dA. Right? So now we have two the important meaning of this Helmholtz energy. First, the Helmholtz energy is the criteria of the spontaneous change, especially at this constant volume, right? And the decreasing of Helmholtz energy, which is the tendency to lower this Helmholtz energy, is a state of increasing this entropy. It's not the internal energy decreasing. So this is the other remarks for this Helmholtz energy. And third is the constant temperature. At this constant temperature, the Helmholtz energy change equal to this maximum work at this constant temperature. Right? There's three things we have talk about. Yeah, so there's one more slide. So that's why the relation between this A and maximum work can be defined as the maximum work is the delta A, and delta A is the delta mu minus T delta S. So this is the kind of relation now we have. Okay, so let's solve examples about this Helmholtz energy. So when this 1 mole glucose is oxidized to carbon dioxide and water at 25 degrees C, according to the equation of this one, and during the process, the calorimetric calorimetric measurement at 25 degrees C gave this kind of value, which is the delta mu is the minus 2808 kilojoule per mole, and delta S is the plus 182.4 joule per kilomole. And in this kind of situation, how much of this energy change can be extracted as a heat at constant pressure, right? And work. Let's solve it. So I'll give you a few minutes to solve this solution, and then yeah, after a few minutes, let's solve together. Okay, so let's solve together. So I just okay. So right. So they'll read this example again. So what is the condition? We have 1 mole of glucose, C6H12O6, and this glucose is oxidized to this carbon dioxide and water at 25 degrees C according to the equation, which is the glucose solid plus 6 oxygen gas. So transit to this 6 carbon dioxide gas and 6 the water molecules. And during this process, we just measure this calorimetry. So using this calorimetric measurement at this 25 degrees C, and this gives this internal change delta mu is the minus 2,808 kilojoule per mole. And this entropy change is the plus 182.4 joule per kilomole. And in this kind of situation, how much of this energy change can be extracted as heat at this constant pressure? And the work. So let's see. So we know that this heat releases at this constant pressure is equal to the value of delta H, right? Right. So we need to relate it to which is given. I mean, so we suppose that all the gases in these gases are perfect. This is kind of assumption. And we can use simply delta H equal delta mu plus PV, and PV can be written as the nRT, and we will put this N as VG. And for the maximum work available from the process, we can use the W max equal delta Helmholtz energy. Why? Because this is a temperature is the constant, right? 25 degrees C and 25 degrees C. So we can use this equation. And because this, how can I say? So right, so let's see the temperature change. There is no temperature change, right? And this is the constant, and Vg equal also 0, right? This is kind of number of molecule, and there will be no change of the number of molecule, so that's why the delta Vg will be 0, right? So that's why here this will be 0. So then we only have these two things, right? But now we have this value by this calorimetric measurement. So that's why this delta H equal delta mu equal minus 2,808 kilojoule per mole. So therefore, at this constant pressure, the energy available as heat, right, which is energy change can be extracted as heat, will be 2,808 kilojoule per mole, right? And what about work? Right. So we can simply use this equation because this is a constant temperature. So maximum work will be equal to this delta A. So delta A is called delta U minus T delta S, right? And delta U is the minus, right? And T is a 25 degrees C, and this is the 298 Kelvin. So they try minus Kelvin. And what about delta S? Delta S is the 182.4 joule per Kelvin and more, right? So you can simply calculate these two things. Then we have this value, right? So there's some mistyping. This is the kilo. The K means the kilo. And this is the Kelvin, the temperature. This is the unit for temperature. So that's why if we calculate these two things, then we have minus 2,885 kilojoule per mole, right? Because there is the Kelvin can be removed. Then you can simply multiply this two value, and then you have this equation, right? So therefore, the combustion of 1 mole of glucose can be used to produce up to 2,885 kilojoule of work. Right? Okay, so what do you think about this kind of example? So actually, the solution of this this kind of example is quite simple. So maybe you will think this is so simple, but yeah. So the key things of this kind of a thermodynamics problem is the how can I say, the interpreting this kind of the problem question. So to solve this one, so you have to extract this kind of equation, right? And this kind of definition from this work. So to solve this one, so you have to know this kind of definition, and then you have to have kind of a sense to choose some the appropriate equation, which you have already learned in the previous chapters. So actually, that kind of things is difficult. Not but this solving the process is difficult. So yeah, so anyway, so that's why you have to have some kind of understanding of this all this kind of process. Okay, so yeah, so now you understand about this kind of a problem, and let's move on to this Gibbs energy now. Okay, so previously we have also learned about this Gibbs energy. is quite similar with this Helmholtz energy, but this is the condition at this constant pressure. So what this means? So so some remarks on this Gibbs energy is that this a constant temperature and pressure, that kind of chemical reactions are spontaneous in the direct direction of decreasing Gibbs energy. Yeah. So this is the important concept. So as in this the Helmholtz energy, for this Gibbs energy, so that reaction will be spontaneous when that kind of Gibbs energy is decreasing. So that is the one remarks for this Gibbs energy. And Gibbs energy is related to this non-expansion work, right? Expansion work is related to this delta Helmholtz energy, and non-expansion work related to this delta G. So as I told you, this non-expansion work is kind of some additional work, which is not the expansion work, which is the including this volume change. So the relation between this Gibbs energy and maximum non-expansion work can be defined as the maximum additional work, which is the non-expansion work. We say this W add max is given by the change in the Gibbs energy. So D add max equal dg, and the W add max. So W add max is the delta G. So why that kind of things happen? So because this enthalpy is U plus PV, right? For general change in the condition. The change in enthalpy can be defined as the dH equal dQ plus dW plus PdV, right? You have learned about these things in the first law of thermodynamics, right? Yeah, so in the previous class, we have learned this kind of things. Where is it? Yeah, so we have learned in the previous classes. So this is, how can I say? So this is kind of the expansion work. PdV, dPV is the expansion work. And then this is the additional works, right? So the corresponding change in the Gibbs energy equal the defined as the G equal H minus Ts is the, we can simply write this dG equal the H minus TdS, right? dTs equal TdS minus S dt. Right? And because the H equal this one, and you can simply put here these terms, and we have dq plus dw plus p dpv minus tds minus s dt, right? And when the change is isosomal, we can set dt equal 0, right? Because this is isosomal, there is no temperature change. Then we can simply remove this one. And finally, we have dg equal dq plus dw plus dpv minus tds. Right? And when the change is reversible, then dw equal dw reversible, right? Because this is reversible. Going back should be same. And dq equal also dq ref, and this is the equal to tds, right? You will see in our previous class, the in reversible process, dq ref equal tds, dq, right? So that's why for reversible and isosomal process, and dg equal tds, right? So because dq equal tds plus dw ref reversible and dpv minus tds, and you can simply remove these two things. Then finally we have dw reversible plus pdv. So the work consists of expansion work, which for reversible change is given by minus pdv, right? And possibly some other kind of work, for instance, the kind of the additional work. So the additional work we denote as the W add, right? Therefore, the dPV equal PdV plus VdP, right? So we now from here to here, and this dPV equal PdV plus VdP, right? And the work is the minus PdV plus the W additional work. Then you can simply remove these two things, right? Then this the W at max and VDP only the remained, right? And if the change occurs at this constant pressure as well as constant temperature, we can set dP equal 0, right? Then, right? Because dP equal 0, we only have additional work is dg, right? So we only have the W additional work equal dg. So that's why the non-expansion work, maximum non-expansion work equal to this delta G. Right. So yeah. So yeah. So this is kind of containing many assumptions, but this is why. So we can say this the W at max is delta G, right? So maybe the start of this justification is because U equal Q plus W and PV. So that's why dH equal dQ plus dW and dPV, right? Then we can put this our all this already known concept to this system, then we can finally have the equation, right? So the thing is, we have to appropriately choose which terms we can use, and then in terms of especially when you solve this kind of examples, then we have to select one of this equation and one of this kind of the definition to solve that kind of equation. So for that, we have to have some kind of concept of this kind of terms. And then we have to reorganize this kind of the variables or terms which is given for this problem. And then using choose some kind of the equation or definition which can solve that kind of problem using some previous already given that the value constants or values. So that kind of things is the process to solve this the thermodynamics related to the problem. Okay, so yeah, so I just want to summarize of this Helmholtz energy and this Gibbs energy. So now we have learned about this. So let's read about this thing again. Okay. So now I think if we read now this one, and then you can understand more about that things. So Clauss inequality, okay, so implies a number of criteria for spontaneous change under a variable condition. So in terms of depending on this variable condition, we can use these two different terms, which is the Helmholtz and Gibbs energy. Such things we have learned. And spontaneous change process at this constant temperature and volume is related to this Helmholtz energy, the decrease in Helmholtz energy. And then the change in Helmholtz energy is equal to this maximum work accompanying a process at constant temperature. Now we know this one. And in case of a spontaneous process at constant temperature and pressure is accompanied by a decreasing the Gibbs energy. And the change in the Gibbs energy equal to the maximum known expansion work accompanying a process at the constant temperature and pressure. So this is the key point, what we learned through these classes, right? So we also have defined the kind of Helmholtz energy as like this, and Gibbs energy like this, right? So Helmholtz energy is the U minus Ts, and Gibbs energy is H minus Ts. So anyway, this is always related to this entropy and enthalpy. So these two things we have learned. And this Helmholtz energy is the related to this maximum work. So dW max equal dA. So especially at this constant temperature. So we can simply calculate this work, maximum work can be done for this the system can be solved by using this Helmholtz energy concept. Right? And we can also calculate this maximum additional energy at this constant temperature and constant pressure by using this delta G. So this is the basics of Helmholtz energy and Gibbs energy. Okay, so I think we had better have a break here and continue the class further after the break. Okay, so before the break, I'll just give a quick summary in Korean. 네, 그래서 이번 시간에는 지금 헬몰츠 에너지와 깁스 에너지에 대해서 여러분하고 이야기 나눴습니다. 그러니까 이 자발적 반응이 일어나는가 안 일어나는가 하는 그거를 우리가 판단하는 거예요. 그러니까 이게 왜 중요하냐면 뭐 여러분 나중에 뭐 어떤 화학 반응을 한다던가 예를 들어서 뭐 어떤 것을 이렇게 만들 때 이게 그냥 우리가 쉽게 만들어질 수 있는 것인가? 그러니까 어떠한 뭐 새로운 뭔가 일을 하지 않아도 그러니까 예를 들어서 뭐를 집어넣었을 때 두 개가 이제 뭐 새로운 물질을 뭔가 만들어져야 되는데 그러려면은 이제 자발적 반응이 일어나야 되는 거죠. 자발적 반응이 아니라면 자발적 반응이 일어나도록 뭔가 새로운 걸 계속 넣어줘야 돼요. 자발적 반응이 일어나는 조건이 되도록. 그래서 이 자발적 반응이 일어나는가 안 일어나는 것을 판단하는 게 사실은 어떠한 뭐 재료를 만든다던가 어떠한 화학 그 반응을 이렇게 이해하는 데 있어서 굉장히 중요합니다. 네. 그래서 우리가 이런 그런 자발적 반응이 일어나는가 안 일어나는 걸 판단하는 여러 가지 이제 뭐 크라이테리아들이 있는데 그 중에 이제 기존에 이제 우리가 이제 좀 뭉뚱그려서 얘기했던 게 클라우시스 이퀄리티라는 걸 우리가 배웠었죠. 기존에. 그래서 엔트로피를 배우면서 우리가 ds-t분의 dq 값이 0보다 큰 경우에는 이게 뭐 자발적 반응이 일어난다 안 일어난다 뭐 이런 거를 판단할 수 있는 우리가 식으로 사용할 수 있다 이렇게 배웠던 건데 이것들이 이제 좀 더 특수한 조건에 대해서 나타난 게 바로 헬몰츠 에너지와 깁스 에너지입니다. 그러니까 사실 깁스 에너지가 나중에 좀 더 많이 쓰이는데 이게 왜 그러냐면 깁스 에너지, 그러니까 결국 헬몰츠 에너지라는 게 설명했다시피 그 컨스턴트 볼륨인 컨디션에 대해서 헬몰츠 에너지라고 얘기를 하고 있고 깁스 에너지는 이제 컨스턴트 프레셔일 때 이제 깁스 에너지를 이제 이용하고 있는데 대부분의 우리가 이제 그 반응, 그러니까 현실에서 일어나는 대부분의 이제 반응들이 뭐 그런 약간 그 대기업 공기 중에서 이제 반응이 일어난다고 생각 많이 하잖아요. 그렇기 때문에 대충 이제 보통은 이제 컨스턴트 프레셔인 경우가 많은 거죠. 그렇기 때문에 우리가 이제 깁스 에너지를 생각을 할 때가 많죠. 근데 만약에 프레셔가 막 바뀌고 막 그러는 경우에는 이제 또 뭐 헬몰츠를 써야하는가 뭐 다른 어떤 또 복합적인 추측을 써야 하지만 대부분은 이제 그냥 그 대기 중에서 일어나기 때문에 이러한 깁스 에너지를 더 많이 접하게 되죠. 근데 뭐 어느 게 중요하다 안 중요하다라고 얘기하는 건 아니에요. 둘 다 어쨌든 많이 쓰입니다. 그래서 이제 그거를 얘기할 때 있어서 뭐 이러한 이게 데피니션을 여기서 이제 말씀을 드렸던 거고요. 네. 결국 뭐 여러 가지 얘기를 했지만 결국은 이거를 말씀드린 거. 그래서 이거를 이제 말씀드린 거죠. 그렇죠? 그리고 깁스 에너지는 요거를 말씀드린 거고. 네. 이 부분에 대해서 이제 여러분이 어느 정도 이제 이해를 하셨을 거라고 보고요. 이제 뭐 이거를 설명하면서 조금 더 이제 뭐 그 얘기를 드리기 위해서 뭐 어쨌든 헬몰츠 에너지에서 말씀드렸던 거는 이제 헬몰츠 에너지가 이제 줄어드는 게 자발적 반응으로 이제 가는 건데 그게 뭔가 이제 뭐 내부 에너지가 뭐 줄어들었다든가 그거를 얘기하는 거 아니고 특히나 왜냐면 볼륨 자체가 컨스탄트 하잖아요. 헬몰츠 에너지가 그렇죠? 컨스탄트 볼륨이잖아요. 그렇기 때문에 뭐 내부 에너지의 어떤 변화를 나타내기보다는 이 값이 엔트로피가 증가해서 그러니까 무질서도가 증가했기 때문에 뒤에 감소하는 거다. 헬몰츠 이게 되는 거다. 요렇게 이해를 하셔야 된다는 걸 이제 말씀을 드렸고요. 그리고 맥시멈 워크 이제 요러한 어떤 관계가 성립을 한다. 뭐 이렇게 쭉 다 이렇게 계속 설명을 했지만 결국은 여기서 하고 싶은 말은 요 관계가 성립을 한다. 이렇게 뭐 정의하는 거는 그냥 여러분이 그냥 알고만 넘어가시면 되고요. 뭐 요거를 막 여러분에게 과정이 어떻게 되고 뭐 이런 거를 해라 뭐 그렇게 강요하지는 않습니다. 근데 이제 이런 걸로 인해서 이렇게 되는구나. 결국 여러분이 이제 이해하셔야 될 거는 이게 이렇게 관계가 된다. 단순히 외우면 사실 잘 까먹고 뭐 그렇잖아요. 그래서 왜 이렇게 되는가를 뭐 좀 보시는 게 좋겠다 싶어서 밑에 과정을 넣은 거고요. 네, 뭐 같은 얘기한 거고, 뭐 예시를 풀어줬죠. 그러니까 계속 저희가 예시를 계속해서 여러분하고 풀고 있는데, 이 예시들이 결국은 다 어렵지는 않아요. 막상 딱 보고 나면, 이 방법을 보고 나면 사실 되게 다 간단한데, 여기서 여기로 넘어오는 게 어렵거든요. 그래서 이런 걸 하는 감이, 그런 감이 좀 있어야 이 문제를 좀 풀 수가 있는 그런 거죠. 그 얘기 잠깐 드렸었고, 그리고 깁스에너지도 이제 마찬가지죠. 깁스에너지 동일하죠. 깁스에너지가 줄어드는 방향으로 자발적 반응이 발생한다. 어쨌든 이런 결국은 깁스에너지가 작아지는 방향으로 어떤 반응이 일어난다. 뭐 그런 거 말씀드렸고 이제 깁스에너지는 이제 그 에너지 중에서도 그 뭐냐 E라고 관련된 거에서는 이제 그 논 익스펜션 비팽창일의 어떤 최대값이 깁스에너지의 어떤 변화와 같다. 그러니까 constant temperature고 그러니까 조건이 여기 있어요. 그러니까 여기 보면 그 constant temperature, constant pressure일 때, 그렇죠? 여기 보면 constant temperature고 constant pressure일 때 dT가 0이어야 되고 왜냐하면 우리가 이거를 유도했을 때 사용한 조건이 이거거든요. dT가 0이고 dP가 0인 경우 0일 때 우리가 계산한 거기 때문에 그래요. 그래서 이 뭐냐 additional work의 맥시멈 값이 델타 G와 동일하다. 저것들을 여러분 이렇게까지 했었죠. 네. 그래서 요게 사실 되게 많이 쓰이는 개념 중에 하나이기도 해서 여러분이 이 부분은 조금 잘 이해를 하고 넘어가시면 좋을 것 같고요. 그래서 네, 이거를 여기까지 하고 오늘은 마무리를 하도록 하겠습니다. Okay, so thank you for your attention and see you in the next classes. Okay, thank you very much.